This is Sanjay. For everyone who doesn't know who Sanjay is, can you give me a quick background on what you do and who you are?
Yeah, my name is Sanjay. I'm a Nozzle narcissist, I guess. I really like nozzles. No, I helped found one of the founders and directors of a company called E3D, and we make extrusion systems for 3D printers. So, um, we're famous for hotends, and the filament drive systems, as we call them, or extruders. It's a very confusing naming structure that we've evolved over the years. But in the round, I would say that our fundamental purpose is to understand the underlying physics and operating mechanics of extrusion systems and 3D printers, and then resolve that to practice. By manufacturing and building extrusion systems, and our optimization target is impact. So we're not trying to produce the highest performance extrusion system. We're trying to produce the extrusion system that has maximum impact for human progress, I guess. So that's why we often target things like cost and user experience over some raw performance numbers. And that's kind of our strategy going forward. Optimize for impact.
Yeah, and when it comes to optimizing, you guys just announced Revo, which is the mythical V7 that everyone's been waiting for. So,
yeah, even we called it V7 for a while, and then it was kind of like, well, this isn't a hot end; it's an extrusion system for hot ends, and so you can put it on a multitude of different extrusion systems. But just like V6 is an ecosystem, we didn't start out designing it like that. It just kind of, and then we made a longer heater block, and then we made hardened steel nozzle. Whereas Revo is more like, we started out with the vision of producing an ecosystem that solves many of the hang-ups and limitations in the V6 ecosystem. So right from the start, in terms of performance numbers, the spec was better than or equal to V6. So our starting first assumption is that we don't need to improve performance much beyond V6.
which is true. Like everyone loves those speed benching videos now where people are doing benchies in under 5 minutes, but the vast majority of people are printing nowhere near those speeds.
Precisely, and this is the vast majority. And so in terms of how do we optimize for impact and have the greatest impact, Revo is faster. It prints a bit faster, and that is intentional, and we've made it faster to the extent that most FDM motion systems have gotten faster. But there's no point making it 3 times faster when the motion systems in 95 percentile of 3D printers are going 1.5 to 2 times as fast. This is just not really, that's not going to help anyone. But the real big spec points of Revo are no tools, no experience, no documentation. Right. And this is the coolest thing about having it on like the trade show stand, showing it to people, is someone who has literally never seen it before, and you whip it out. And I think I did this to Dan Barus of Slice. He'd never seen it before. He sidles up to the stand, and I put it in his hands. I'm like, rock on. And we have a good relationship with those guys. I say, they're competitors, but sportsmanship,
professional relationship.
Yeah, and we take the piss out of each other on the internet here and there, and it's good fun.
You gotta have fun. You gotta have fun.
Yeah, but also, they give credit to us for what we've done, and where we've been inspired by Slice in the Revo system, we intend to give credit there as well. So we have a respectful competitor relationship, I'd say. Anyway, so I dumped this thing in Dan's hands, and I'm like, go change a nozzle. And I give him another nozzle, and he's never seen it before. Now, Dan
reaching for the tool.
Yeah. Dan probably knows something about hotends, I imagine. But I'm taking the piss now. immediately able to figure out how to change a nozzle. There's nothing, no tools, no anything. Everything's happening cold, so you no longer have to touch 300 degrees C things while they're running, while the electricity is live pumping heat into the heater and grab it with pliers. That is not a thing. And it's not a thing that we think is appropriate to expect of users in the current state of our technology. That's just not, that's not going to cut it.
As things are starting to get a little bit more mainstream, you have people that have no background. Like for a lot of people, 3D printing is a hobby, right? You get into it because
It's
the printer itself is the hobby. But now you're seeing people where it's like, oh, I just want one for work so we can print some models of things we're designing. We're an architectural firm. I don't know electronics. There's magic pixies in there. I don't want to touch that. So here's a wrench, heat it up to 300 and change the nozzle, but don't accidentally crush this wire or you break it. That's great to be gone now.
Yeah. I just imagine walking up to any other piece of electrical equipment, even advanced. Imagine going up to a good milling machine or just a gaming computer. That's the level of people that we're dealing with that build their own gaming computer. Still, it's far. You don't need tools. You can pop in RAM. You can snap out M2 SSDs.
Yep.
That's what we wanted to introduce for Revo, and that's the intent. So, in order to do so, we had to develop a few fundamental technologies. And I guess the thing that we're here to talk the most about is heaters.
Yes, the heaters.
There are other things in Revo. There's the nozzle changing system. There's how we've taken the parts and done metal-to-metal sealing to join up together this single filament path. But
yeah, so we'll try and cover a few things, but we are time limited. So we'll start with the heater itself, because you've released plenty of information so far on the Revo. And for those who haven't read the blog post, there's videos on it already. There is content out there already for those generalized about it. But a lot of questions have popped up about the heater, because you now have this all-in-one circular heater that surrounds the nozzle brake, although it's the Revo nozzle now. I believe that's the correct term. But a lot of people are comparing it to, there already are circular heaters on the market. The Maxiwot, for example, that's been around for a few years. So if you can give me a quick breakdown of what current heaters, the existing heater cartridge we're all used to, how those are made and how those work, and then compare that to what you've done different with Revo.
I wonder how quickly I can do this. Okay, so a heater cartridge, you get a nichrome wire, it's a nickel chromium alloy, and you wind it around a little matchstick, kind of like this iPad pencil. And you wind it around, so you have this thing. It's called a mandrel, and then you take a piece of metal tube, and let's.
Need props. We need props.
So you've got this thing that's now wound with wire. And the wire, it's actually got a hole straight up the middle that you pass one of the wires up, and then you take it and you put it inside a metal tube, and you hold it kind of in the middle, and whatever you do, you don't want it to touch the sides, because this is the glass with steel, and that will short and conduct the electricity. So you hold it in the middle, and then you kind of pour magnesium oxide around and pack it into place. So magnesium oxide is just a powder, and it's a ceramic that's fairly thermally conductive, but it's also very soft, kind of like chalky and talcum powder-like. And so then you take this whole little assembly with the wires and stuff, and you might weld some lead wires on at this point, but you get the idea. You got this thing. And then it goes into a big machine that basically crushes it. And that, it goes, you might start with an 8 or 10 millimeter heater, or 10 millimeter tube, and then crush that. And that compacts the magnesium oxide ceramic around the coil. But that compacting is quite a chaotic process. And it stretches the wires and the joints, and everything's deforming. I mean, you're just like, there's entropy everywhere. You're just like crushing
It's hard to keep it within a certain spec, I guess.
Yeah, I mean, if you ever looked at heater cartridges, a lot of the cheaper ones on the ends, they're kind of tapered in, because it's fed into a machine with rotating hammers around the outside that kind of like like this, and you feed it in, and it squishes the whole thing around. But yeah, the tip gets squished more than the back, so you end up with this. To combat that at E3D, we then centerless grind the heater cartridge afterwards to bring it back into like a well-specified circularity tolerance, leaving good kind of surface finish and cylindricity.
Yeah, because you could see that. I've seen that like on high quality cartridges. They got the ground finish, and then you go buy the cheap 5 cents each pack of 20 off AliExpress, and they're all just mangled steel essentially in the shape of a tube.
Yeah, and they're quite pitted, and you can see the
but the internals is pretty much the same across the board, right? The internal, how it functions, is pretty much the same from every manufacturer.
Precisely so. Manufacturing process. I mean, there's actually just kind of one company that sells all the machines to build it, and all the mandrels and the classic Chinese industry. It's all kind of interconnected. Moving onwards, the Maxiwot Heater. The Maxiwot Heater is a heater cartridge, bit longer, bit thinner, and then you bend it into a circle and you push it into a metallic housing. I think theirs is copper with nickel plating. No, it's aluminium. It's aluminium. Then it's welded shut with a plate-like construction.
Okay.
And cables get added on, and so on and so forth.
So they're basically the same, just in different shapes. So now for the Revo Heater. So what's the Revo Heater? How is that different?
Yeah, so we don't rely on nichrome wire. We start with something a bit like this. Very thin-walled alumina ceramic, which is a highly thermally conductive ceramic. It's not dissimilar to what you might make a ceramic knife out of. It's like that kind of grade of engineering ceramic. I'll check myself on that. But you take this and then we print on the outside. And it's kind of like silk screening. It's a process where it's a screen print, right? So, but instead of screen printing like white ink onto a PCB, we screen print a tungsten, a paste, essentially, a tungsten ink around the outside through a kind of stencil. And that stencil is made with a photolithography etching technology. So it's very cheap and easy to make yourself a new track. And so you can like rearrange the heat and the size of the tracks, so their thickness, their concentration and where they are. So you can literally paint heat onto the
so you have so much more control over it.
Right. And so if I want to put like 50% of the heat here in the bottom third, and then the rest of it up here, you can do that. Or you want to put it all on the left and a bit on the, you can do that. And then again, it's kind of like PCB tech in that we then put a layer over the top, but with vias in it essentially. So there's another layer, a capping layer, that is, again, it's a ceramic, so that you protect the printed ink, but it has little holes in it that are like windows to the crack. And then we braze, kind of like soldering, just a higher temperature version of soldering. We braze wires to it. And so you end up left with something like this, that has wires brazed to the side, and this beautiful printed track. So if you get a Revo and look really closely at the sides, you can actually see that gray trace winding its way around, like a serpentine trace. And if you get one of these before it's turned into a final Revo heater, and you shine a light down here, it's all translucent, because it's like after you lay it up, all these inks and such, it goes back in for another sintering process. Sorry, forgot to mention that. But what that does is it means that the cap layer and the ink, it all kind of sinters together, essentially melts together. And so instead of having an assembly that's made of crushed up together powder, you now have a solid state system. Like it's a fully bonded solid state integrated heater circuit.
Nice.
And
so
instead
you
of it being
everyone should be pretty much exactly the same. You shouldn't be seeing any variances. They should all be pretty much like identical now going forward, correct?
The variance is about the same compared to or the standard deviation from the mean is the same, but the mean is always in the middle.
Okay, I see what you mean.
Whereas if you get a batch of heaters, sometimes they're like shifted up and down because the machine that was pulling out the nichrome was pulling out a bit more that day. It's really getting into the weeds here, but the the really, really cool thing is that these heaters, a solid state heater, that there's real deep magic, and you're printing it around the circle. It's kind of like how you screen print on mugs and stuff. It's similar to that.
Okay.
I won't go into too much detail, but it's freaking cool. Now, these are positive temperature coefficient heaters, which is a fairly new thing in the world of 3D printers. Definitely not new to anyone that does any kind of electronic heating system. What this means is, as the heater gets hotter, its actual power output drops off. So when you reach around 350, it's dropped down to maybe about 15 watts. So you go from 40 watts at 20 degrees centigrade to something like 50. Don't quote me on those numbers, but it's significantly
as it gets hotter,
it
draws less power, basically.
Yeah. And this isn't like a controller that's built in. This is fundamental to the materials. It's as the atoms and the tungsten particles and the ceramic expand, there's less conductivity inherently in the material. So this is a really incredible safety feature because you're not relying on a thermal fuse, you're not relying on an algorithm. And don't get me wrong, we've got some amazing algorithms that really look after your heater incredibly well and know how it should be behaving and if there's any deviation from that. All of that still works with these systems. I think there could be some optimizations to be had, but all of that still works. What we're adding is a fundamental to the material, deep, inherent safety, which means that, you cannot melt these things down. And I've taken a 12 volt, 40 watt Revo heater and hooked it up to, I think my power supply only went up to like 32 volts. So I just gave it everything I had in a big bench power supply. And yeah, it got hot. A heater cartridge in that same situation would be in the 250 watt region.
Oh yeah,
that's how much power it'd be dumping out because it's a square factor of voltage, right? Whereas this heater was only drawing 60.
Wow. So let's give you a scenario here. Okay, I built my printer. I bought a Revo. I got a 24 volt Revo, 24 volt power supply, but I was cheap and I used an ANET board. And I just went and had my MOSFET blow, and now it's getting fed 24 volts all on. It's a MOSFET fault, so thermal runaway isn't going to protect me. Yep. So how hot is it going to get?
I wouldn't like to quote a number, but what I will tell you is it will not melt down.
Yes.
So it is, I'm not going to say impossible, never say never, but I have tried to melt them down using all of the power supply and all of the voltage into the lowest voltage heater, and all I can get is the most extreme of extreme errors. So your MOSFET blows, you installed a 12 volt heater in a 32 volt system, and it blows open, and your power supply is just able to dump in the current. It doesn't melt down. It just sits there. It'll glow a little bit in that very, very extreme situation, but it doesn't melt down. It doesn't drip molten aluminium or pop a nozzle that is over the flash point ignition temperature of PLA down into your print, and that's the scary bad failure mode. You don't want that. Nobody likes that. So that failure mode with Revo is orders of magnitude less likely to happen. I'm going to say impossible, but
extra safety is always good. Extra safety is always good, and it doesn't cost you anything extra. It's drop-in and it's solid state built into it. You don't need any firmware. You don't need any chips or anything. Right. It just does it.
Yeah, and this really helps for things like UL and CE certification and the like, where you can't just have two algorithms running on one processor and say that I now have two redundant safety systems. They would class that as one. So oftentimes you need two redundant in order for them to be accepted as compliant devices. You need that. So on heaters, on things that get hot. So that's, yeah.
Okay, now you said it was a 40-watt heater. Was that kind of just what it ended up with the form factor you had and how you were designing the heater itself, or were you aiming for a 40-watt heater? Because I know it's what a lot of people call a standard flow heater, and people want that high flow. So is there the ability to go bigger or smaller, or you're kind of limited by your size and form factor for the heater size?
Oh, I mean, the great thing about this process is it's like software definable. So if we wanted to make a longer one and print more track and add more power, we can go wild, right? You want a 16 volt, 44 watt heater? Like, yeah, sure, we'll print you one of those. No drama. Which is cool. That's fun. But yeah, we started with 30 watts. Ooh, pardon me. And because of the inherent safety, we were able to just add a bit more power on, and there was still bags of headroom left within the safety margin and the PTC effect. So yeah, let's throw some more power in, because the beautiful thing is that it means that you can add more power at the times when you need more power and tune the PTC curve such that you get less power when you really don't want it. And so like it's a really neat little bit of like designer materials almost. Yeah, and then moving onwards, I guess so we've got this little ceramic heatery thing with all of its glory inside, and people have done similar metal ceramic heaters before. So credit where credit is due. Like the Delta printer guys put theirs on a hot end. And I think there's another one that I don't recall. But we're not the first to use a metal ceramic heater. What I think we are the first to do, though, is to take that and integrate it into a system that is a truly fully capable all-metal hot end system. So previous metal ceramic heater-based 3D printer heaters, they would bond the heater to the nozzle with something like a high temperature epoxy or silicone adhesive. So essentially, it's an organic molecule, right? And organic molecules don't do well above 250 to 300 degrees centigrade. That's just a kind of fundamental limit of the carbon-carbon bond breaking point. So we knew right from the start we had to bond the heater to this metal thing, and that turned out to be one of the most significant challenges, actually, because we take our heater and we pop it over something that we call the mandrel, which is a turned metal part, and that's essentially the kind of equivalent part to that of the heater block. But now we can make it on a lathe, which is great.
Yeah, because everything on the Revo is lathe work now, right? Everything is lathe work. You're not doing any flats. It's all lathe work. So
all day long.
So manufacturing, you've cut down all that extra manufacturing steps and everything, and now you have one machine running all day.
And so for people at home that aren't familiar with like production machining and the differences between them, when you're looking at a heater block, you take a slab of metal, you put it in a machine that has a motion system, probably not dissimilar to your 3D printer. Instead of a nozzle, you've got a milling cutter, and then you come along and you blat away a bunch of material. But then you have to do some flips, and you have to have maybe a special vise that you've already pre-cut, like we call them soft jaws, to hold and like you have to go through. And if you look at a heater block, it's got holes coming out of all the sides, and you've got to go through it.
Years ago, I actually machined a V6 block out of, I think I used Amco. It was something we use in molding at work. It's like a brass aluminum or a brass copper alloy. So I machined one of them on a Bridgeport on my own. And just making one, yes, on a Bridgeport, it was still like hour and a half, because you have to figure out how you're holding stuff, and then it's got to set up, and then you got to cut the slots for clamp, which I just gave it to the guy on the wire ADM to do for me. But
yeah, and like that will not do at the, like, when we're into making thousands per day, which is what we've been building the production line to support. And so when you have a lathe and a turned part, you have something called a bar feeder. And a bar feeder is kind of like the magazine in a gun, in that you have tons of bars all stacked up like this. And the one at the bottom is being fed into the machine, the chuck, kind of from the back, right? And so it's being fed out, and you put out just enough to make one Revo mandrel, and you come along, and this is spinning. And so you come along with your tools and you do all your stuff and drill some holes from the end. And then actually what we do is we have a second chuck over here, and it gets cut off. And so now you've got your little piece over here. You come and do some backside chamfering. All of this is fully automated. So you've got something like 9 axes, but it's no human interaction. There's no flips to do, because the machine is just handing off the parts and doing its stuff all day. You've got 2 heads working in tandem, running in parallel, and these little parts then get dropped off onto a conveyor belt that just drops them there and feeds them to the end, and then they go into a part washing process to remove the oil that's being sprayed around everywhere. This is a huge deal. This is a really, really big deal, because a heater block is actually like the most expensive part of the hot side, I think.
Which most people don't realize. It's just a block of copper or aluminum with a few holes in it. Whoop-de-doo. But when you think about how it takes to make that,
it's the dumbest part. Yeah, I like it's really, it's my fault. But
well, you didn't know what 6-7 years ago when you guys were designing that thing. Right?
Well, originally when I was designing it, it was designed around a piece of standard extruded grade aluminium that you can get, which is 16 by 20 or something. And the intention was that you would saw off a chunk and do the things and kind of bar feed it. That never actually came to pass, and we ended up machining them out of billet, because that's the way you do things.
And all the wasted material too.
Yeah. So this is dramatically more efficient. It's more accurate. We can set the machine running these and then turn off the lights and go home for the weekend. And it's just got a stack of... These bars are 3 meters long. So if you think about a 3 meter long bar and how many little Revo heaters you can fit in that, even with the waste and all the rest of it. And then you've got like 10 of them stacked high. That's cool. That's really
cool. Lights out machining is awesome once you get it set up.
Yeah, and I mean, the machine that makes these, we use the same thing as you used to make Swiss watches, or Japanese watches, technically. It's a Japanese branded lathe. And I kid you not, when it's making these things, it's quieter than most 3D printers, despite the fact that like there's carbide being shoved into spinning metal at like 5,000 and ripums. You're getting, it just sits there and sings. It's a thing of beauty. Swiss machining, there's basically just high pressure oil everywhere. Like every single one of the tools has through coolant and like tiny micro channels basically that are blasting. I think it's like somewhere in the order of like 50 to 100 bar oil being blasted at the point where the cutting is happening to lubricate, cool, and blast away the chips. And all the drills have the same channels going through them that blast out all the chips. There's oil everywhere, just like tons.
These machines are enclosed.
Yeah. And then you even have to have what's called mist extraction because you go in really fast with a high-speed drill or something, and you generate mist, and that mist will you kind of creep out of the machine, and don't breathe this, and also you don't want oil all over the floor, so you have big extractors. Like, we don't peck. Like, no. Pecking is for amateurs. Like, when we're going with the drill, like if you've got 200 bar oil, the chips are coming out, right? And you just like stub drill straight in, one and done. Yeah. The one that blows my mind the most is when we start the first cut on a Revo heater is to turn it into this kind of top hat shape with the so what you've got is this kind of top hat shape thing, and then you put the heater ring around that. So it's like the ring is sitting on the brim of the heat of the top hat, encompassing the cylindrical upright bit. And when the tool comes in, it basically does that entire pass in a one and done. Like, it's kind of like 3-4 millimeters deep, and it's just like gone.
Yeah. Now, what material is the heater block made out of? It's a brass copper, right?
Yes.
Okay, so aluminum's gone.
This is a real aluminium's out. It's a copper alloy.
Okay.
I mean, it's over 95% copper, I believe. I guess majority copper. I'm gonna shut my mouth because that's a really big deal. Anyway, that's really cool. It's really, really cool. Yeah, that one really gets me. That really gets my juices going.
Metallurgy, yes.
Yeah. I mean, right to the point where we're considering like doing a custom run and tweaking. So, and this is where we're getting like really freaking cool. Like, with like designer materials, like, you know, from the friggin'. Well, no, actually, with Obsidian, it's now down to the point where the coatings, we're not just like arranging atoms, we're literally fucking like unpicking the handwriting of God, ripping apart the nuclei of atoms, producing plasmas, right? And we turn methane, like cow farts, and then we like plasmarify them with pixie dust and then recondense them into diamonds. Like, that is alchemy at its like most fundamental level. And it's like
DLC coatings are awesome. DLC
it's not even chemistry. Awesome. It's just like it's like deeper. It's Anyway, minor rant. Like I enjoy that. Anyway, but we're considering doing a custom run of material to tweak some properties, but that's another story. Now you have your heatery thing. This that we talked about, this PTC, but it's a very thin ring. It's like a 0.5 millimeter thin ring, and you can almost see through it. It's kind of translucent. And you drop it onto this metal part that's been produced on this bar-fed process, printed thing that's sintered, solid state, onto bar-fed little round widget. But now you have a gap between the center, so just as your ring going on, and like you've got a gap between the heater and the thing in the middle. We cut some channels and stuff into the side of the top hat, which is where the wires and the thermistor kind of sneak up, and a few other features. Like there's a little ridge that allows us what we call the strain relief, which is that sheet metal part that gets clipped onto the top at the end. You take that and you sneak a thermistor in down the side into a special channel, and the head of the thermistor has a tiny little pocket where it kind of nuzzles in and gets all into place, and the strain relief is in place. And then we have this again. This is again another real nice bit of designer materials. Is this adhesive that we took some existing recipes that a ceramic adhesive company had, and we modified them so that the process was faster, and that the adhesive itself was more thermally conductive. Again, just really, really neat, like real nitty gritty, and so that's a kind of a cement, and it gets kind of injected into the gap. So you kind of inject it into that gap, and it then fully wets out and fills that void in the middle. And it's the interfacial layer between the heater and the thing that you kind of want to heat in this case, which is that mandrel that you want to get hot. There's a whole curing cycle and process, and what you end up with is the heater being completely bonded. It's not like they're just in contact. They are one piece now. That heater is now a single, fully bonded object.
Yeah, it's not coming apart.
You can, with a hammer, maybe, it'll come apart. I mean, I've taken my fair share of them apart. It just,
under normal operations, it's not coming apart.
Under normal operating conditions, no, it's not coming apart. And that is actually one of the other big features. Is I'm sure many of the people, if you've gotten this far into the video, listen to me ramble on about this, you've almost certainly broken some thermistor wires. Like, if you stayed long enough for this, you've been playing this game long enough that you've broken some thermistor wires. We've all been there. Thermistors are delicate, and these wires are all kind of small, and everything is small. Everything is so small. It's a real pain. But one of the really cool things we've done is this strain relief thing on the top. So clipped onto the central core, the solid metal core, is the sheet metal part, and the wires for both the heater and the thermistor come up, and then they get this thing has wings, kind of like a crimp connector that you crimp on a Molex or DuPont header. We actually kind of took that and looked at it and did that scaled up a bit, and it grabs all of those cables together into a single bundle, and we crimp that around it, and so it's holding on to all of those wires for you, so you can't pull the thermistor and rip its legs out of it. So
that's already saved me once. That thing has already saved me once.
This is really important because 3D printers move, and wires and moving gets very difficult very quickly. So we needed a system that didn't allow the wires. If you've done a mediocre job of strain relieving the system yourself, it has a lot more resilience in terms of cable strain and flexion and fatigue than any of the systems that we've seen in the past. So the robustness level is through the roof. Because I often hear and see people say, so if the thermistor legs break, then I'll have to replace the whole Revo heater. Yes, that is technically correct, but also we fixed the problem of the thermistor legs breaking, which is the real fundamental underlying issue, by fully integrating it and providing this steel armored cable strain relief exit system.
It does flex a bit, because I've had people ask me about it. It does. You can bend it if you need to, if your tool head needs the wires to be at an angle. Don't do it often though, but it can bend if you need to.
Right. So it's malleable. It's not a spring steel. It's not a hard steel. As with any kind of crimp connector thing, it needs to have an amount of softness so you can squeeze it into place and have that kind of bite and cinch down onto the cables. And so, that exit wire thing, it has an amount of, you can take it and bend it into the right kind of shape-ish within certain limits to suit where the wires have to go in your printer. But afterwards, it is a rigid body in effect. It is not designed to allow exceptions, but it is, you can kind of get the wires to go and exit as you please.
Okay, and this is all in-house too, right? Everything for this new heater, this is all in-house.
Yeah, from the bar, the actual heating element printing and sintering process, that is not done in-house. That is subcon. But everything after that, including the machining at the moment, we're machining them all in-house right now. This has been the biggest challenge that in terms of things that we've developed at E3D. This has been the biggest challenge to date by far. It's like a Revo heater is just a cylindrical heater around another cylindrical part. You can go on CAD and draw one of those up, and it seems like lots of renders of Revo-alike heaters have suddenly started to pop up from other folks. So, it's very, very easy to take a round heating element and draw it around a thing and then make a prototype. Producing 1,000 of those a day and building the machinery to produce 1,000 of those a day, that is a different problem entirely. And that is what we've been solving over the last couple of years. So Rory...
How long has V7 Revo been in development? Because it's a
very slippery question, because it was like it evolved and it kind of hoovered up technologies that were around, and it was kind of this snowball of just like, how are we going to do this and that? And we made a couple of big design pivots early on. How long has it been going on? It's a blurry line, but it's not less than 2 and not more than 4 years, I'd say. It's around the 2 and a bit-ish mark, I'd say.
So that's it for the heater. Did you want to talk about the quick change system itself?
Yeah. The nozzle changing system is different to most others out there in that there are no threads on the heater to nozzle interface. What we have instead is the heater is spring-loaded downwards, and then the cylindrical portion of the nozzle goes up into a closely toleranced hole inside of the heater, and the spring pushes the heater down onto the kind of collar of the nozzle, that knurled part that you grab onto and turn. It's being pushed down. So there's a face-to-face contact there, and the cylindrical interface contact, whatever you want to call that. Have you read the YouTube comments lately? Folks are there like, but the heat might not be able to get from the heater to the nozzle well enough. Is that...
It works. Somebody tell Sanjay, he might not know this.
We didn't think of that. No, we have entire machines for testing that this works. We have this incredible thing. It doesn't even have a name. It's just called the rig. And the rig is an extruder and a hot end, just with F1 grade telemetry. So I think that we're sampling the load cell at 1,000 hertz to measure the forces. There's temperature measurement. There's encoders on the filament. There's encoders on the drive wheels. Everything is being watched to within an inch of its life. And then we push plastic through it and we watch the data. And you can see exactly how much melting you are doing. A Revo absolutely, definitely meets and exceeds the specification point for as good as, if not better than V6. Even in the absolute worst case tolerance scenario that we allow when quality controlling these for the largest internal diameter heater and the smallest internal diameter thing, and a bunch of other conditions being in their worst possible theoretical state, it still melts more plastic than a V6.
Are you able to say what the tolerance is supposed to be for the sizing between the hole in the heater and the barrel of the... Okay, fair enough. But it's like a slip fit, ream fit. It's a tight tolerance tool.
Yeah, that was one of the harder aspects.
When the heater heats up, because I know when it's cold you can go in there and you can loosen it by hand, but when the heater heats up, does it expand into the core, or are they still slip fit when they're both hot? because metal expands. So
Still,
is it filling that?
still slip fit. Yeah, no,
Okay.
it's still slip fit throughout the whole
Okay.
range of its existence.
Because somebody was asking me that, I'm like, I'm not going to go in there and grab it at 300 degrees. So we'll let Sanjay answer that.
No, but yeah, what is nice is you have the silicon sock around that, and so whilst grabbing the thing while it's at 300 degrees is not going to be a fun experience. It's kind of like a "ooh, ow," rather than an instant blistering and kind of crispy bacon fingers.
I'm sure everyone has an M7 hex nut somewhere, burned somewhere.
Oh yes, oh yes, and I think like safety and making sure that we're doing things right is one of the most. It's one of my favorite parts of the system. Is that once we've built this entire heater, it then goes on to a quality control rig, and a quality control rig doesn't just measure the resistance of the things and say, "Is this good?" We run it exactly like it will be run by you and your printer. So we take that heater and we connect it up to a system that heats it up and ramps it up hard all the way up to its maximum temperature, turns on fans, blast cools it, rinse and repeat a whole bunch of times, temperature holding. And this whole curve, we know what it should look like when we do all of these like things, and we measure data along the way, capture all of that. We know how a heater should be behaving correctly and operating correctly, and we test it like you will use it. So we put it through the same set of challenges, as it were. Yeah, train like you fight, fight like you train. And so the quality control rig, it works like that. And all of that data, just like Prusament, like we're going to put our money where our mouth is. And so you will be able to go and all of this data is serialized. Every single heater is serialized. As they're going through all of the manufacturing steps and processes, it's really freaking cool. There's lots of QR codes and barcode scanners along the way for every single little process, the kind of the crimping, the bonding. We're capturing data about all of these things all along the way. And then finally at the end, we capture a whole bunch of data about how this heater is performing and behaving across the whole range of temperatures that it's expected to encounter in the course of its use. And that is really freaking cool, because it's one thing to quality control some spec numbers. It's a completely different thing to actually observe the system in operation and verify that its operation is within bounds of what you are going to do. So this isn't quality control by inference. This is quality control by observation of the true performance of the system. And then we're going to put that on public, so you can go and scan your hot end, put its serial number into some kind of web UI, and the graphs.
So will you be able to pull up like, okay, so this is like the PID values for the heater. Would that be something that would be on there?
We're considering trying to add that, but at the moment, individual PID auto tune would add a lot of cycle time.
Yeah, good point. Good point.
But it may be that we're able to build a system that infers and calculates what the PID set point is and should be. But frankly, when we're running the machine, we just use one set of PID values and everything is totally fine. And PID tuning these things is a piece of piss anyway. It's just it's so ridiculously easy to control them.
Yes, that's one thing. Like they're so, like, obviously I only have the one beta unit, but it's so consistent for like the heat up times, its stability and everything. It's yeah,
they're just like dead nuts on the whole time, and that's because the thermal mass and lag of the system, like where the atoms that are generating heat are and where the atoms that are in the plastic and flowing and taking away that heat, that distance and the amount of like travel and lag between that is just been reduced massively, and we're getting the sensor like right in next to where it needs to measure. And so we've taken a system that was kind of really quite large and bulky and aluminium-y in this whole block, and you had the heater over here and sensor. We've crushed that down by something like 5x is the increase in not heat up rate, but the responsiveness. And those are very different things. But when you look at your graph, if you like request, a ramp to 250, you ramp up really fast to 250, but you don't get that like
overshoot
over the. Yeah, it just goes flunk, and then.
Yep, that is one of the things I've noticed. Is if you got like a Dragon High Flow or some other big blocked heater or hot end, and you have like a 50-watt cartridge in there, it always overshoots quite a bit.
Yeah, you get that boing, and that's because those systems, in control theory, we would call that dead time. And dead time kills control loops. Dead time is just the enemy of it. Like dead time is like backlash in a gear set, right? So this is like the thermal equivalent to backlash. We basically the kind of amount that when you stop adding input in and then try and go in the opposite direction, you end up freewheeling. You turn off the heat, and you don't actually get any reaction until the heat has traveled through the system and stopped traveling through the system, and the actual impact of your change in input doesn't translate. It's like we've gotten rid of the thermal backlash, as it were. At a mathematical level, they're kind of equivalent.
Okay. Now, just go back to the quick change. So we've discussed how the spring mechanism works and all that. Now, for screwing into the heatsink, you went with the Hemera style, where it just screws in. And it's the Hemera. Now, did the Hemera come first, or did you design the Hemera screw-in system with Revo in mind?
Yeah, we didn't design it with Revo in mind, but it was there, and it looked like a good choice, and it meant that we could then go and easily take it and put it on a bunch of systems that have been designed around Hemera brakes.
Like one question I got a lot was using like some sort of, why didn't you guys use like a locking lug system instead of like just like an index and a locking lug? And I figured that was mostly for like manufacturing, because now you got to manufacture inside pockets inside your heat sink for it to index off of and all that. Or is it just simply to keep it compatible?
The getting enough heat from a heater into a nozzle problem is the thing that everyone thinks about when they think about a quick changing system. And they're like, we've got to get all the heat into the... That problem's actually pretty easy. And I mean, it's a big high temperature system, and the plastic's coming in cold, and like, it's a very tolerant system as well. Because if there's, like a little bit of thermal transfer jump, which there isn't, it's, but everyone looks at, when making a quick change system, they get very focused on that. But it's actually the other side of the system that kills you if you go wrong. So if your heatsink and cold side, even for just a tiny moment, just for a second, exceed the glass transition temperature of PLA, that's it, it's game over. And we tried lugs and many, many other things. And we found some things that did work well, some less so, and there are other challenges along the way. Because it's all well and good having lugs, but lugs are not going to transfer heat out of a hot end where the heat needs to get out. And one of the beautiful things about the Hemera brake is the distance between the tube wall at the top to where the heat sink taking the heat off is very low, so you've got this nice thin section. In Revo, it's even better because we make the cold side out of a copper alloy as well, instead of it being stainless, quite similar to the sliced bimetallic heat brake system. We're using a hypodermic needle tube. And I think the way that we're putting them together is quite different, because we have a quite, this metal to metal sealing process. But the thing about Hemera brake that is really neat is also that it has this like top hat brimmer thing, and that does a whole bunch of thermal spreading exactly at the point where you need to get the heat out. Like right at the point where the heat must get out of the tube, you're taking it out sideways with a copper alloy that's then in hard contact with a heatsink. That is the beauty of the Hemera brake design. And then after that, you have threads.
Okay, that's nice. Yeah, that makes sense now that you explain that little the flange there or whatever. So it gives you repeatable for indexing, so you're always gonna have the same tool length, and then also that's gonna dump the heat right into the heatsink right away. Okay.
When looking at the quick changing system, that's the hard part of the system. The bit down below is actually really easy, so we'll just use the simplest possible thing, which is a cylinder and a hole in a cylinder, and not overcomplicate it, because that's actually a very tolerant, easy system to get the heat flowing enough through, because there's huge amounts of heat flux going on, and everything is just fine down there. It doesn't care. It's like running at 200 degrees. It's not. But up there, it's very sensitive. So we used something that we knew worked well, and made it work even better by going bimetallic and using a copper alloy up there. And it also allows for just drop-in backwards compatibility. Or it's not quite drop-in, but it allowed us to very easily adapt Hemera to accept Revo systems. And we had been, for a while, developing a micro hot end based on the Hemera heat brake, which Revo then, and that's kind of the genesis of Revo Micro. It's a long, convoluted, messy development story that I could give you all the lineage and different projects that kind of convalesced into one, but you wouldn't be interested, and it would take a long time.
We would need a flow chart, spaghetti diagram.
Yes.
Now, touching on the Revo Micro there, so at launch, you're going to have the Revo Micro and the Revo 6. So, but a lot of people want like rigid mounting. You've hinted that you're working on other heatsink designs. Are you able to say what will be available for release or after release, or is that still under? And I'm assuming, because the whole cold side's open source. So if you don't put out a Ender 3 compatible heatsink, I'm sure one will be on AliExpress in a month. So
we'd be stupid if we didn't release heatsinks for popular printers, right? That would be a really dumb move. Like that would just make no business sense whatsoever. Like, oh, here's the most popular 3D printer in the world. Would you like people with that 3D printer to buy your product? No, says E3D.
I figured the reason you showed those two off first is they're all made on the lathe, and they're probably just the first to be produced, which makes sense. And they're dropping compatible with the existing ecosystem that uses V6.
Yeah, I mean, you know, I fucking hate groove mount just as much as anyone else. Don't get me wrong here. Like, and we ballsed up groove mount really hard, like twice, I think, by accident. We're really sorry about that. It's like we changed the groove mount standard twice by accident without even really noticing it. That whole shit show's just a mess. And I'm sorry. I'm sorry that it's still there. We gave you Revo Micro with the nice M12 threads. Please shut up about it. I regret it. I'm sorry. We'll never do it again. Just let it go. And like, we've all dealt with it. Like, we've put that behind us now. Like, can we just move on in this relationship and forget about the whole groove mount affair? Okay.
Okay. So expect rigid mounts to be announced at some point.
Yeah. The M12 one is nice because you don't have to come along and do any like drilling and stuff, and so you can make a lot of those heat sinks really quickly. And we're gonna have to make a lot of heat sinks really quickly, and also it's actually a bit harder than it might sound.
Okay. Yeah, because now you're going back into doing operations that aren't just lathe work anymore, for the most part. Depending on the mount you're going after.
Yeah, and also just making it work in a Creality type system. The airflow and it's all designed around cooling a PTFE lined hot end, which just doesn't really care very much about being warm and toasty, or like, does any of the air actually hit the heat sink in the current? Like, yeah, there's intricacies there. We've got getting those ironed out. Like, we're getting there. We're getting there. The main challenge, though, like, eyes on the prize. If we get the whole Revo internal manufacturing process, and this is like incredibly complex, this is the hard problem to solve. And then once we're producing these at scale, at a cadence of 1,000 per day, going off and designing a new heatsink is child's play. I bet even the boron community could design themselves a heatsink.
Yeah, we probably could. Just aluminum.
I jest, but we're just concentrating our efforts on building the really fundamental, critical core technology of the system, and then going out and adapting it and getting it into other machines is an easier problem that we know is tractable. So those are not the problems that you attack first.
Yeah, so I'm going to have to end it there. I do have to go to work now, unfortunately.
Sorry, dude.
I would love for you to come on a live stream at some point, because there's a whole bunch of subjects we never touched on, and that would open for Q&A as well. So you're welcome to come on whenever. We'll work something out for timing, because I know you're 5 hours ahead of me. I'm going into work right now. You're sitting at home, just had dinner. So we'll figure something out. But I want to thank you for spending the time. This was an awesome chat. I wish we could have gone into more. So yeah, thank you very much, Sanjay.
All good, man. I've had fun. And yeah, looking forward to a live stream. That'll be good.
Yes.
That'll be good.
We'll work something out. We'll figure something out, and I'll post about it when we figure something out. Okay. Take care.
Have a great day at work, dude.
Thank you.
Care,
Cheers.
Man.
Bye.